All right. Thank you so much. Welcome, Dr. Ouyang, to the stage on designing GPU native zkVMs and challenges for real-time proving.
Thank you for the hype. Woo! Let's talk about some cool GPU stuff and zkVMs. Okay, let's go to the first slide. Okay, first of all, who is Snarkify? Snarkify delivers highest GPU performance for zk. That's our statement. So who in the audience believes this is a true statement? Please raise your hand. Okay, I see one of my teammates there. So the whole purpose of my talk here is to convince you throughout the talk why Snarkify delivers the highest GPU performance. So hopefully at the end of my talk, you're convinced. Let's start with our Z-Prize winnings. So over the past 2 years, we participated in many Z-Prize competitions, and we are the only team in this industry who has won 6 prizes across GPU, WASM, and FPGA. That means our performance optimization capability is across platform. So we can do browser-side, client-side proving, we can do server-side GPU proving, we can also do hardware circuit programming to use FPGAs. Finally, like at the end, we picked GPU as our betted platform because we believe GPU will win in the Z-Prize high performance computing as a platform. Another point is that if you look at the 2022 winnings as well as the 23 winnings, you can observe a trend because the bottom right one, there is a plunk end-to-end. Because in this talk, I will review the development of GPU acceleration in the ZK field, like the history of GPU acceleration in ZK. It's basically from optimizing small kernels like MSM and NTT, and eventually go to end-to-end proof generation, and finally reaches the zkVM stage. Let's go through it. So a brief history of GPU acceleration in ZK. In stage 1, that's prior 2022, where ZK was just picking up, people were mostly talking about how do we optimize the compute kernels like MSMs, NTTs, with devices like FPGAs, GPUs, or on client-side MSM, etc. After we solved this compute kernel problem, people figured out even if we accelerate those compute kernels very fast to the extreme, immediately other part of the compute becomes a bottleneck. So you actually don't get 10 times speed up just because you optimized MSM or NTT, because the other part of the computation becomes a new bottlenecks. So that's why people shifted to end-to-end zkVM acceleration. So the representatives are like Scroll doing in-house GPU optimization as well as RISC-0. That's 2022 to 2024. Starting from past year, almost everyone was shifting to the RISC-V zkVMs. And there was a performance war between those all RISC-V zkVMs. And who wins the GPU prover war basically wins this performance competition between zkVMs. So we have teams like RISC-0, Succinct, both working on GPU acceleration, and we are also working on zkVM GPU acceleration. I'll talk more about it later. Okay, let's start from stage 1, compute kernel optimization. That's for this example is from our Z-Prize 2022 winning. So this is on CPU side, WASM. I'll compare the CPU optimization with GPU optimization a little bit so that you can know why GPU acceleration is kind of unique. So if you look at the algorithms, the techniques we used here, the basic Peppenger algorithm you may have heard of, actually we need to apply 5 other techniques to make MSM on your WASM in your browser really efficient. By the way, this is public on my head app HackMD. You can easily find it online if you search for it. However, if you look at the GPU optimization techniques, they are slightly different from the CPU techniques, mainly because you have 22 or 100 CPU cores on your CPU chips. However, on GPUs, it's thousands of CUDA cores. Because of this massive parallelization, we actually need to develop new algorithms that works on GPU. That's a key technique we use to ensure your algorithms run very efficiently on the GPUs. So basically, how to map certain compute problem to a massive parallel compute device like GPU. So that concludes stage one, basically optimizing this MSM kernel as well as NTT kernel. Okay, then we go to stage 2, end-to-end zkVM acceleration. This is already in production. It's on explorer.snarkify.io. This shows our production proof generation for the scroll mainnet. We generate up to 50% of scroll's mainnet proofs every day. So the technology behind it is a Hello 2-based zkVM GPU prover. Different from many other proof generation service providers who just use Scroll's GPU prover, we are the only one who has in-house GPU implementation that's actually faster than Scroll's in-house implementation. So we are actually we have the fastest Hello 2 GPU prover in this industry. So in this figure, you can see the proof generated in the past 30 days, as well as the successful proofs generated, as well as our throughput to generate these proofs. So let's dig deeper. Let's look at the performance numbers. On the left, you can see the end-to-end CPU time. The gray area is the quotient polynomial evaluation, just one name, one compute procedure of the compute process. The blue and the green one are weighted generation and lookups and column permutations. You can see that, so the two compute kernels are involved in in several of these compute procedures, for example, MSM and entities. However, if we just solve the MSM and entity issue, it won't improve the end-to-end speed, just because the quotient polynomial evaluation will be the new bottleneck. You can see the pie graph on the right. The time of the gray area got reduced dramatically from more than 1,000 seconds to 36 seconds, mainly because we developed some specific algorithm to implement polynomial evaluation on the GPUs. That's not the MSM kernel or entity kernels I talked about previously in stage 1. That's some new compute challenges we need to solve to achieve end-to-end acceleration. And you may notice that on the right, the blue actually becomes a new bottleneck. So the blue area is faster, but not dramatically faster, because weighted generation is a serial process. It's very hard to parallelize it. But we have a solution now, because when we are working on the zkVM acceleration. So overall, end-to-end, we achieved 3.8 times speed up compared with Scroll's in-house version. We are 40% faster, just from the software perspective. Okay, this is about stage 2. This is another more impressive result about stage 2. You may remember that we reached 3.8 times speed up, which may not be quite impressive. That's because the problem size is very large. That cannot be fitting on a single GPU device. If you look at this problem, on the bottom is a baseline performance, 500 seconds on CPU. The GPU is a typo, by the way. It's a CPU performance, 500 seconds. On the top line is our performance, it's half second. That's 900 speed up, 900 times speed up. Why could we achieve this? Mainly because this problem is small enough. It's a Poseidon hash based Merkle tree proof. It's small enough to fit in a single GPU device, so we can fully utilize the GPU compute to speed this thing up instead of bottlenecked on data transformation on the PCI bus or data accesses between the GPU chip, the CUDA cores, and the DDR memory. So let's look at the proof flow. On the left is the host compute procedure. On the right is a GPU compute procedure. As you can see, the key technique here is to move every compute to the GPU. It looks intuitive and easy to do. However, in reality, it's not, because the naive way to move your compute to a device is actually constrained by the problem size and your memory utilization, memory footprint. For example, if your compute takes 100 gig of memory, you have no way to fit it into one single GPU device. That's the same thing for AI compute workload, right? So when you train a model, the model is so large that it cannot fit in one single GPU device. You have to divide the workload across multiple GPU devices and introduce many cross-device communications. That will become the bottleneck. That's why AI is heavily relying on the communication between GPU devices instead of just the compute capability of the GPU. So for this particular problem, it's a Poseidon hash-based Merkle tree proof. Because it's small enough to fit in a 40 gigabyte of GPU device, we can actually move all the compute to the GPU to really write fast kernels and fully utilize the compute on the GPU. As a result, we achieved 900 times speed up over the Rust CPU baseline. I want to take a moment to comment on the common misconception of hardware acceleration. Because when people talk about some compute-intensive problem, for example, AI or ZK is too expensive, it's too slow, immediately they think of ASIC. Like, let's build a chip. Let's build an ASIC to accelerate ZK. Is that the right solution? So, because people always trace back to, for example, Bitcoin mining when you do all the hashes. They say like Bitcoin mining transferred from CPU to GPU to FPGA and to ASICs. That's why ZK will follow the same route. However, that's not true, mainly because ZK is a memory-bound compute. That's very different from Bitcoin mining. That's a compute-bound problem. Same thing, like let's look at Ethereum mining instead, or AI instead, which are data-bound. That's when GPUs really outperform other devices. That's comments when we look at this speed up we can achieve here just on GPU device without using any specialized chips. Okay, let's look at stage 3. This is hot buzzword right now. Everyone is building a zkVM, and everyone wants to use their zkVM to prove EVM blocks. So this website, ETHProofStog, is already online in production. Currently, there are 3 vendors proving EVM blocks, layer 1 blocks. That's us, Snarkify, and Succinct, and zkVM. It's worth noticing that we are proving real EVM blocks from Ethereum layer 1. That's like production level blocks. People are doing transactions on them. So we can already use current state-of-the-art zkVMs to prove them. The problem is, if you look at the proving time, it's over 4 minutes right now. For zkVM, it's over 17 minutes. What's our goal here? We actually want real-time proving. That means prove every EVM block under 12 seconds within average block time. So how do we achieve that? Let's look at the RISC-V zkVM proof pipeline. This is common to all the Stark-based zkVMs as well as other newer VMs. It's like a shared architecture of the zkVMs you can find on the market. So on the very left, you have your target application program you want to prove, a RISC-V binary. In case of EVM blocks, it's a RE code base that's validating your EVM blocks. So once you have a target program to prove, you load it into a RISC-V emulator to generate all the checkpoints. Once you have the checkpoints, you basically partition the whole execution, the whole instruction set or sequence of the instructions into multiple partitions. And each partition is called a shard, and you generate a shard proof for each partition. And finally, on the right, you aggregate all the shard proofs into one aggregated proof. And in order to do on-chain verification, there's an optional wrapper proof where you converted your aggregated start proof into a wrapped Groth16 proof or Planck proof just for cheaper on-chain verification. Okay, let's look at the shard proof instead. There are 3 sub-steps in the shard proof. One is to, again, you need to emulate all your RISC-V instructions to emit all the events. For example, add events, multiply events, load events, or store events. If you are familiar with CPU instructions, that's what you do. The next step is to generate the traces, basically fill up the trace table with all the events generated. And finally, you can run the mathematical computations over the table to generate your proof. Okay, this is a proof pipeline. Why it's hard to achieve real-time proving on this proof pipeline? When you want to improve the latency of some compute, the most straightforward idea you can think of is to throw in more hardware. Like by increasing the parallelism, you can basically reduce the compute time or your latency. That's happening here because we are doing many parallel shard proofs here, trying to decrease the latency. However, it's not that straightforward because the darker area, the colored area, the RISC-V emulator is a serial process that's running on a single CPU core. There's no way to parallelize it. Like out of the 4 minutes of the proving time, probably you spend 1 minute or 2 on this serial process. That's why only just looking at this RISC-V emulation process, this colored area is 10 times slower than real-time proving. So we have to solve this problem first before we are any closer, any chance closer to real-time proving. So here are the 2 challenges we identified. One is what I just mentioned, the serial RISC-V emulation problem on a single CPU core. The other problem is the PCIe bus bottleneck of trace data transfer. Because as I mentioned, we generate, once we emit all the events, we fill the trace table. We actually need to transfer the trace table to the GPU, then generate the shard proof. Then we are bottlenecked on the PCIe bus. No matter how fast your accelerator is, no matter you are using a GPU, a FPGA, or even an ASIC, you are bottlenecked on the same problem because you need to transfer your trace table to the GPU or to the accelerator to accelerate it. So we have to, no matter which team are working on these problems, we have to solve these 2 bottlenecks to really achieve real-time proving. The good news is that there are solutions, and we know the solutions. Unfortunately, I cannot disclose more details at this moment because we are actively working on it right now. Our internal roadmap is to deliver real-time proving by June 2025, and we are publicly announcing it with Ethereum Foundation and with every of our partners. We are quite optimistic on this target given our current progress and what the progresses we have made so far. And yes, stay tuned. We will give you a surprise by June 2025. We call this DeepSeek moment in ZK. At that time, people will suddenly realize ZK is not as expensive as they think, and ZK is not as slow as they think. It actually can be fast, well, quite affordable. My prediction is that for the second half of this year, people will have a new view or perspective of the cost and performance of ZK. Therefore, there will be a new wave of ZK adoption. Even though we are kind of at a bottom of ZK narrative right now, however, I believe Snarkify is here to change this. We are pushing the boundaries and taking ZK to the next level. Okay. Thank you, everyone. I'm Jiannan Ouyang. Stay tuned about our progress. Thank you. Any questions? Oh, please.
One, two, two, one. Thank you for the presentation in the first place. I'm a colleague of Mike Voronov, to be honest. So my question is, do you share the architecture of your circuits?
Do we share the architecture of our circuit?
Yeah, the last diagram that you showed, yes, this one, RISC-V emulator.
Yep.
So this is a circuit. And I suppose you have a multiple purpose-built circuits that actually emulates RISC-V architecture, ISA.
Oh, I see. The circuit-specific stuff is actually on the trace generation side. Okay. So once we generate all the events, then we map the events to the circuits. That's on trace generation, basically filling up all the trace tables. Okay. Before that, it's a pure RISC-V emulator, basically executing RISC-V instructions and record all the metadata we need. Mm-hmm. So that's like ZK agnostic. It's not even relevant to ZK. It's just execute the instructions and taking notes of the information we need. Then we fill this information into the trace table, which are circuit specific.
Mm-hmm. And the second question comes to my mind. How do you deal with the random access verification?
Random access, that's a memory argument stuff, right?
Yes.
Our position is like we don't invent cryptography right now. So we don't roll out our cryptography.
You don't mind this part. I get
We
it.
are following existing zkVMs design. For example, SP1 implementation. That's what we are working on right now. We use their, I believe, is a multi-set hash-based memory argument. And later we could follow RISC-0 zkVM specification. So what we do here is follow their spec and making it as fast as possible on GPUs.
Okay, I get the point. So everybody follows RISC-0.
Yes.
SP1 and you.
They are the leader. Yeah.
They're the first. Yeah.
Yes. We respect their work.
Absolutely. Thank you very much.
Yeah, thank you. Thanks for the questions. Hey, thank you again. Yeah, I can